All right, hello and welcome. Today we're going to do something kind of cool. We are going to climb down the computer's secret ladder. I mean, think about it. You click something on your screen and magic happens. We're going to trace that single click all the way down to the tiny electrical pulses in the hardware that make it all work. So let's start the descent.
I mean, it's really the central mystery of computing, isn't it? You have a thought, you express it with a click or by typing something, and somehow this machine, this box of wires and silicon, it just gets it. It understands you. So how on earth does a computer bridge that massive gap between our human world and its own world of pure logic? Well, computer scientists actually have a name for this exact problem. They call it the semantic gap. And it's a perfect name for it, because on one side, you've got these powerful, really abstract human-like languages, things like C++ or Python. But on the other side, you've got simple wires and gates that only know two things, on or off, 1 or 0. And for a computer to be useful at all, that gigantic gap has to be bridged so perfectly that it becomes totally invisible to us. So how'd they solve it? It's actually a brilliant divide and conquer strategy. Instead of trying to make one giant leap across that gap, which would be, basically impossible, they built a ladder of abstraction. It's a whole hierarchy of levels, and here's the clever part. Each level only has to know how to talk to the level immediately below it. That's it. And this is our roadmap for the journey down. We're going to descend through all these levels of abstraction, starting way up at level 6, the user level. That's where we all live, and go all the way down to level 0, the actual physical digital logic. A good way to think about it is that each level is its own little virtual machine, whose only job is to translate instructions for the next guy down the line. All right, let's kick off our descent. We're starting at the very top in the world that's familiar to every single one of us. So, level 6. This is where you are right now, watching this. It's the world of applications, icons, windows, the stuff you actually interact with. You're using a word processor, you're playing a game, you're browsing the web. And at this level, all the mind-blowing complexity happening underneath is almost completely hidden. It just works. Okay, so take one step down that ladder, and you find the tools that build all those applications. This is level 5, the high-level language level. This is where programmers work, and it's the very first place where a human idea gets translated into a structured language that a computer can start to understand. And the magic word at this level is abstraction. A programmer can work with concepts like variables or functions without having to think for a second about what physical memory registers are being used. They don't need to know. All that heavy lifting is handled by a special program, either a compiler or an interpreter, which basically acts as a translator, converting their code for the next level down the ladder. And that brings us to level 4, assembly language. Now, this is a super critical step. You can think of it as a middle ground. It's not really human readable, but it's also not the raw ones and zeros of the machine. It's the essential bridge connecting those two worlds. And here is the absolute key feature of assembly language. There is a perfect one-to-one relationship with machine code. Every single command in assembly translates directly to exactly one instruction the machine can understand. There's no guesswork, no ambiguity, which makes that final translation step incredibly straightforward. And this table just lays it all out perfectly. Check it out. On the far left, you have a super simple command in a high-level language. A equals B plus C. Easy enough, right? But look at the middle. That's the assembly language. It has to break that one idea down into very specific steps. Load the value of B into a register, load the value of C into another one, then add them together, and finally store that result back into A. And then on the far right, that's what the computer actually sees, the raw ones and zeros. Okay, so we've successfully translated our command into the machine's native tongue. Now we're diving even deeper, into the layers that actually manage the computer's core operations and bring all that code to life. We've now arrived at level 3. And this is the home of the operating system. The best way to think about the OS is as the computer's master traffic cop and general manager. It's the one that takes all the machine code instructions from all the different programs and makes sure they all play nicely together and run smoothly without crashing into each other. And believe me, the OS is juggling a lot of things at once. It's the reason you can have your web browser, your music, and a game all running at the same time. That's called multi-programming. It's also the reason one buggy app can crash without taking your entire computer down with it. That's memory protection. It really is the unsung invisible hero of modern computing. All right, dropping down to level 2, we hit something called the Instruction Set Architecture, or ISA. And this is it. This is the true native language of the computer's processor. Every single thing we've talked about so far eventually gets translated into this language. When it comes to software, this is the end of the line. There's nothing lower. So if that's the final language, who or what actually reads it? Well, that is the job of level 1, the control level. The control unit is like the conductor of an orchestra. It reads the sheet music, which is the machine instruction, one note at a time, figures out what it means, and then points to the right sections of the orchestra, the hardware, to make the right sounds at the right time. And when you're building a control unit, you basically have two choices, and it highlights this classic engineering trade-off. You can hardwire it, which means building it directly from physical logic gates. This is blazing fast, but it's really difficult to change later. The other option is to microprogram it, where a tiny, low-level program inside the chip interprets the instructions. This is way easier to modify, but it comes at the cost of being a little bit slower. It's always this battle, speed versus flexibility. Okay, we've almost reached the bottom of the ladder. We're about to leave the world of programs and instructions entirely. Our next step takes us into the physical reality that makes everything, and I mean everything, we've talked about so far possible. Welcome to Level 0, the digital logic level. This is the ground floor. This is where all that beautiful abstraction ends and raw physics takes over. Every command, every piece of logic we followed down this ladder finally becomes a real physical action right here. And you know what this entire level is built from? Just two things: gates and wires. That's it. Gates are basically microscopic switches that perform incredibly simple logic. Things like and, or, and not. And the wires? They just carry the electrical signals, the ones and zeros, between all those gates. Every single complex layer we've just journeyed through is built from the ground up on these unbelievably simple fundamental parts. So there you have it. We've gone from a simple click on a screen all the way down to an electrical pulse and a wire. Now, let's just step back for a second and appreciate the absolute genius of this design and really think about why this whole hierarchy matters so much. You know, this quote really nails it. The computer isn't just one giant, complicated machine. It's better to imagine it as a whole stack of virtual machines, one built on top of the other. And this wasn't some happy accident. It was a deliberate, absolutely brilliant design choice. And here it is, the most important takeaway from all of this. The true power of this ladder of abstraction is that it lets us completely forget about the immense complexity of the levels below us. A game developer writing code up at level 5 doesn't need to know or care about how the control unit at level 1 is designed. And that right there, that is what makes the entire world of modern computing possible. This elegant structure, this ladder, has served us incredibly well for decades, and it's allowed for unbelievable innovation at every single level. But it does make you wonder, right? As our technology and our needs keep evolving, what will the next layer of abstraction look like? What will a potential level 7 hide from us in the future?